The name of our project is Project Car Harvest, and a brief description is a tile that harvests energy using automotive transportation without adding carbon emissions. Okay, so here's a brief outline of our project. First, we're getting to meet the team. Okay, so I'll let the team leader introduce himself first.
Hello, my name is Pablo Salvador. I'm an electrical engineer. I'm part of the hardware team.
My name is Raul Pet III. I'm an electrical engineer, also part of the hardware team.
My name is Drew Bato. I'm a computer engineer and I'm part of the software team.
My name is Anthony Dochai. My major is computer engineering and I'm also part of the software team. Okay, so what motivated us to start our project? So the big picture, we decided to create a tile that when you apply mechanical pressure, this would generate electrical energy that could be used for household commodities such as lighting a light bulb in your household. And we got our inspiration from a company in Britain named Pavagen. And they're a company that converts footsteps into energy through the use of Pavagen tiles. So basically Pavagen created what's called a Pavagen tile that when you step on, this mechanical pressure would engender electrical energy that could be used for Bluetooth beacons, so for your phone, and lighting. But we're not going to use Bluetooth beacons. So our originality is we're going to use wheels, not footsteps. So we're not going to be stepping on the tile with our feet. We're going to be using wheels, so basically a car. And we plan to do this on a larger scale. So Pavagen does this on sidewalks, so for civilians. When civilians walk on this Pavagen tile, that would generate electrical energy from the mechanical stress, but we plan to do it on roads for cars. And this can be used to reduce generation loads from power plants. Okay, so this is our AHP diagram, which stands for Analytical Hierarchy Process Diagram. And our final goal up there is to build a harvesting tile. That's our final goal. So we had to take into account the cost of manufacturing. We're only allowed $250 for this project. We also had to take into account the longevity management. We only have 2 semesters to complete this project. And we also had to make a UI for this project as well as hardware module implementations. So we bought an Arduino board. That's our microcontroller for now. We talked to Professor Wang. I have looked for alternatives to microcontroller use because we don't think that Arduino is sufficient enough to complete the rest of this project. So we might switch to PCB board or something else, or Raspberry Pi.
Okay, so our project summary. So basically the idea is to create a tile that'll convert mechanical pressure into electrical voltage. So we had the idea to basically make each tile 12 feet long to cover the span of a single lane on a road, and we would have it a couple of inches, not maybe maximum a foot wide, just for the electrical components to be inside the tile. So we had this idea from basically, like, take LA for example. Like, they have 7-lane highways going to and from downtown LA. So imagine how many cars drive on that road every day. Imagine having a tile every 100 feet on that highway. How much voltage could you create just from harvesting, just from putting tiles down and create energy, instead of generating more power that these local communities could get from harvesting energy. So our societal impact would be a system of tiles installed, the amount of power generation and transportation is greatly reduced. So the amount of cars that are driving are not going to stop. Like, people are still going to use cars, people are still going to use buses to get from point A to point B on their daily lives. That's not going to stop. Like, people might not use fossil fuels because there's always law and restrictions on that every year. So, but nobody's going to stop driving. So what we're doing is we're trying to take from that system without adding anything to generate that. So, so the societal impact, the negatives, these tiles could break after a certain speed. So if someone doesn't follow the speed limit, it could break the tile and cause delays. So that's one of the negatives. That's the realistic negative. So the global impact. So we're harvesting energy on roadways, and it'll cause to take more energy out of the system without adding any energy to produce it. And this will cause for a reduction of power generation and a reduction of carbon emissions. So it'll reduce costs for the power generation companies, it'll reduce costs for the energy distribution companies, and it'll cause for a more like, it's not a renewable energy thing, but it'll help reduce the already generation and distribution that we already have today.
Alright, so our design requirements, for our design requirements, this is for our 40% completion of our project. And for our hardware aspect, we had to power up a light bulb, and the numbers up above are the parameters that had to be met. And for this software aspect of our project, which was basically reading the values, it was basically contingent on our hardware parameters. And bringing it back to the big picture of the piezoelectric tiles on the road, this is our marketing engineering matrix. So for our marketing requirements, we had to make sure that our installation of the tile was pretty easy, so it didn't cause a huge obstruction in traffic. And for maintenance, say if it had to break or upgrades, we had to make sure that it was fairly easy to do those things, along with not intruding with the flow of traffic as well. And the reliability, we had to make sure that, as he said, the speed of the cars, it could handle the weight of several vehicles, and various weather conditions. And as for the cost, it's basically aligned with the rest of the engineering requirements as well.
Okay, so for our objective tree, once again, our objective is to build the harvesting tile, and we need to implement pressure sensors. So basically, this tile wouldn't work unless it sank down. So when you apply the mechanical pressure, that sinkage would generate the electrical energy. So we have to implement pressure sensors and stress test the tile to make sure it works. We have to create a user interface and a database for the UI, which we've done. We purchase and build a microcontroller, which is our Arduino board, and read voltages per second. So basically, we connected a voltage sensor to our Arduino board, and this allows us to see like the voltages to make sure everything is working.
Okay, so this is basically a system description and the architecture of how our system will work. So there basically, think about it as there are two inputs. So there's the client input, and then there's the actual mechanical stress input. So the client input, the client will only see the user interface. That's what the client will see. The client will see how much voltage is being created on a per second basis. That will, that'll be its system on itself. The only thing that connects the two systems are the user interface and the actual Arduino board. So if you look from the bottom up, that's the actual mechanical process. So it'll go from the pressure plates that someone will apply pressure to, will go to the transformer, which will go to an inverter, which will go to the voltage sensor and the microcontroller. That's the Arduino board. So that will talk to the user interface, and those will go back and forth on a per second basis. And then each of those will go to its own database to store and also to compare later on to see, because the whole purpose of this by generating electricity is to show the efficiency. So we want a system that is more efficient, and if we do multiple iterations, we want it to be more efficient than the previous one. So the client will only see the user interface, and the user interface will talk to the Arduino.
All right, so related theory, current, power. We use transistors and MOSFETs. We calculated the values of the current at the base and the collector of the transistors, and the current and the power at the capacitor. We got these values through the testing that we did. We were primarily concentrated at the collector of the transistors, because that's where the current will flow into the MOSFET. Then we use a transformer. That transformer would then step up the voltage to 120 volts AC and power up the light bulb. Also, we did the base current to see if we get any saturation, which we didn't.
Okay, so for our key design modules, like I said in the beginning, we need to apply mechanical force. So this project wouldn't work unless we have wheels that would apply mechanical force on the tile. So that leads to the input force, which leads to the circuit that Pablo has created. He'll demonstrate that later in the hardware video. That circuit is connected to the Arduino, or more specifically, the voltage sensor that's connected to the Arduino that monitors like the voltage of the light bulb and to make sure that it works. And we have that on a per second basis, so we'll also show you that in the software video. That connects to the GUI, which connects to the MySQL database, which we've also created. And in the future, we can create other applications. We can connect to other applications. Okay, so this is our functional decomposition level 0. Like I said, it's applied mechanical pressure from the vehicle's wheels, to the harvesting tile module, and generated DC power, which we monitor using the voltage sensor. And this is our level 1, so the mechanical pressure would be connected to the inverter. That inverter would power on the light bulb, and that connects to the Arduino voltage sensor to make sure that it works, basically. That if we get a voltage like higher than 7, basically that light bulb will turn on and that'll show that it works, and we can monitor that as well, which we do in the video you'll see soon. That connects to the user interface, which connects to the MySQL database, where we can store all these values from the voltage database in Arduino into the MySQL database.
So we reference our circuit to this circuit right here. Like I said before, they use a DC battery. That DC battery is connected to the transistor, and the current from the collector goes into the capacitor. Then that current is filtered and goes into the gate of the MOSFET. Then the drain current goes into the transformer and turns on, steps up the voltage to 120 volts AC, 60-50 hertz. This is what we got from our testing the results. On the left-hand side, we see the Arduino voltages. You see the voltages going from 0 going up to 4.4 to 6.9 and then dropping down. The reason for that is the oscilloscope right there. Going back to the circuit, the parts from the transistors to the capacitors acts as an astable oscillator. So when one point is high, the other is low, and vice versa. That way, when we put both the graphs together, they become steady voltage.
So what we have here is our project schedule and our timeline. So we reached our milestone of creating a circuit that can power up a light bulb using a DC power supply, which is also connected to the Arduino and the SQL database, which we completed the first semester. During the winter, we're going to try to upgrade the hardware and software aspects of our project. And during the second semester, we're going to start constructing the tile itself and completing the rest of the software aspects of the project. Over here, we have our cost analysis, and on the left side is our experimental part of it, which is our 40% completion. And on the right side is our practical part of the project. And the reason there's a few less components there is because we're going to attempt to construct / program the rest of the components needed for our project.
You have to escape the presentation to show them.
It was working yesterday. We kind of need to show you both videos, so let's hope this works. Sorry for the delay. Here are the videos.
So as you can see here, that's the oscilloscope connected to the circuit. The circuit then goes to the transformer. Transformer turns on the light bulb. The reason for using a battery is because our piezoelectric piece only outputted 0.7 volts DC. So in the future, we plan to implement the piezoelectric part with the tile to a boost converter, hopefully stepping it up to 7 volts, which starts on the light bulb. And then here's our software component.
So as you can see, these are displayed on a per second basis.
Conclusions and future work. We were able to get our preliminary circuit to work with the power supply instead of the piezoelectric part. Like I said, our part only was able to output 0.7 volts when put through specific pressure. We had enough data in terms of voltage and current to see what powers up the step-up transformer. We found that out to be 5 to 7 volts with a current of 0.5 amps. We plan to better understand how the project can be implemented in the real world. As you can see, we're using a regular small transformer. For us to implement this into the real world, we would have to get connected into the power grid and be able to be in phase. We plan to finish the UI, connect the UI to the database, replace the power supply with our piezoelectric piece, build the boost converter, and get enough current and voltage to power up our transformer. And our end results, we would like to power up 5 to 7 light bulbs with our finalized circuit. A regular household has 5 to 7 light bulbs. Not all are being used at the same time, so hopefully we plan to do that.
Okay, so some of these are software codes. This is the software code of the voltage sensor. I'm going to explain the first part. So the in offset 20 is just showing that the code works. Basically, if the Arduino board is not connected to anything, it'll show a voltage of 0.20. But when it's connected to Pablo's circuit, that's when it jumps up to about 5-6 volts, as you saw in the video. And down here is the delay 1000, which matters the most, basically out of the whole code, because this displays the voltages on a per second basis.
Okay, so this is the UI code. So we use a program called Qt. And so basically what this shows is that it takes, because we have the Arduino connected to a voltage sensor, we have, basically this code is showing that the voltage sensor is connected to the circuit. So that'll show in that, basically that pop-up. So it goes, and this is a fixed size pop-up that can show up to 7 digits. So when the Arduino is connected to the circuit, it'll give that 0.2 to show whether it's on or off. That will not be affected in the UI. So whether it shows the 0.2 is within the Arduino, which will always output a 0 in the UI. And then that basically is what the client will see. The client will only see that box on a person, and it'll refresh as the Arduino refreshes. So when the Arduino refreshes, it outputs that voltage into the UI, and then this UI will, it hasn't been done yet, but it will be connected to a MySQL database where it will store every single voltage on a per second basis.
Okay, so some standards of our project was to establish proper code to track the DC voltages values of the circuit. So that was through the voltage sensor in Arduino, which you saw before. And then creating the proper circuit to successfully light our light bulb. We had many errors in lighting the light bulb, but we finally got it to light. And establishing a secure connection between the UI and the database. So we want to connect Jude's Qt UI to my SQL database. Some constraints were connecting the user interface to MySQL and the Qt constraint, so the language. And then one of our codes that we have to abide by when considering this project is the National Electric Code, which is it's short for NFPA 70. and it's a standard for the safe installation of electrical wiring and equipment in the United States. So basically, if you're dealing with super, super high voltages, you need a license to do so.
So back to the big picture of the piezoelectric tile on the roads, the ethic issue that closely related to our project was to hold paramount the safety, health, and welfare of the public, which can be found in the Code of Ethics written by the National Society of Professional Engineers. And as I said in the matrix, we have to make sure the installment tile doesn't cause a huge obstruction of traffic, durability of a tile, ensures the safety of everybody driving on the road, and if we have to have maintenance or improvements on the tile, we have to make sure the flow of traffic isn't as great as it should be as well.
Questions?
Thank you very much. Questions?
Yes.
Very interesting concept. I'm still not clear what your tile looks like. It's piezoelectric material with wires connected to all your electronic components. Is that the idea?
Yeah, so we haven't actually made the tile, but we've created the components for the tile.
Yeah, right. But now, if you put these down, for instance, in the Northeast,
Uh-huh.
first of all, there's wearability of the tile, which was mentioned, how long will it last, but also what about plowing the roads? Would that strip out all your tiles off the road surface, for example?
Well, the thing is, these tiles would sink into the ground, so I don't think that would have an effect that much. So I don't think, yeah, they wouldn't be plowed if they sink into the ground.
And also, like we mentioned earlier, it should be easily able to install. So if anything, if they had to do maintenance or anything, they would disconnect the circuit from the tile. That way, if they had to remove the tile or plow or whatever the case may be, it wouldn't affect the tile either. Because the circuit's the one that's making the conversion from DC to AC. Any other questions? Oh, all right. Thank you.
Thank you.